During this lesson, we performed the transition from Chapter 2, dedicated to the study of linear maps, to Chapter 3, dedicated to the examination of systems of linear equations. As in Chapter 1, I prepared a list of questions that you should be able to answer if your knowledge about the concepts that we have seen in Chapter 2 is solid. It is very important for you to test your knowledge by trying and answer all these questions, for example, by working in groups. If you are unable to answer the questions confidently or have any doubts, take the time to revisit the specific concept in your notes or review the related videos to ensure that your understanding is clear. Before passing to Chapter 3, it is worthwhile testing your understanding of the concepts of Chapter 2 with these 3 exercises. As I did for the exercises of Chapter 1, I will read with you the exercises and then I will also give you hints in order to solve them. As always, I underline that it is very, very important that you try and solve the exercises by yourself before looking at the solution that I will provide. Okay, let's start with exercise 1. Establish if the following linear map f from R3 to R4 written like this is 1-to-1, onto, or an isomorphism. The answer to the question of whether f is onto or an isomorphism should be immediate. In fact, you don't have to perform any calculation, you just have to remember the results of section 2-3. The answer to the question is f 1-to-1 can be answered thanks to the result contained in theorem 233. So my final hint is to take a very good look at section 2.3 and in particular at theorem 233 and then to try and solve exercise 1 before looking at the solution that I will provide in this video. Here's the solution to exercise 1. The answer to the question, is f an isomorphism, is immediate. In fact, we know that there can be an isomorphism between vector spaces if and only if they have the same dimension. But f is a linear map between R3 and R4. R3 has dimension 3, R4 has dimension 4, and so f cannot be an isomorphism. Moreover, from this result here, we have that f cannot be onto either. In fact, a linear map can be onto if and only if the dimension of the range vector space is less than or equal to the dimension of the domain vector space. But in this case, we have dimension of R3, which is the domain vector space, is strictly inferior than 4, which is the dimension of the range vector space. So the only property that f can have is being 1-to-1. To check if our linear map is 1-to-1, we can use this theorem here, which says that f is 1-to-1 if and only if the images of the vectors of a basis of R3 is a free family in R4. Notice that this theorem doesn't specify the basis that you have to choose. In fact, you can choose whatever basis of R3 that you wish. However, if you want to minimize the computations, as we have seen many times, you choose the canonical basis of R3. This is the wise choice to perform. If we apply the linear map f to the 3 vectors of the canonical basis of R3, we obtain these 3 vectors here. As we have seen several times, in order to check if these vectors are linearly independent in R4, we have to perform a generic linear combination of them, and we have to impose that this linear combination is the null vector of R4. If the vector equation that we obtain is satisfied only for 0 coefficients of the linear combination A, B, and C, then the vectors are linearly independent. To do that, we know that we have to translate this vector equation into this system of linear equations. If you follow the very easy computations that I wrote, you check that indeed all the coefficients must be 0, and so f is 1 to 1. Let's now discuss exercise 2. Given this real matrix here, find the linear map F associated to A with respect to the canonical basis of R3 and establish if F is 1 to 1 or on 2. Here's the solution of exercise 2. First of all, we notice that since the linear map is square of dimension 3, this means that it can only be associated to endomorphism of R3. Thanks to what we have seen in chapter 2, we know that the endomorphism of R3 associated to the matrix A with respect to the canonical basis of R3 for both the domain and the range is such that if we apply F to the vectors of the canonical basis of R3, we obtain the column vectors of A. This means that we know how F acts on the vectors of a basis, and we know that this information allows us to extend F to the whole R3. To do that, we apply the practical method that we have seen in section 2.3. And we find that F applied to the generic vector of R3 has this expression here. If you replace these vectors with the columns of A, you find that F of x, y, and z is given by this vector here. So this is the endomorphism associated to A with respect to the canonical basis of R3. Now pay attention, we have an endomorphism and we have the explicit expression of a matrix associated to it. What can we do with that? Well, we can compute its determinant. We know that if the determinant of A is different than 0, then F is an isomorphism. Instead, if the determinant of A is equal to 0, then, thanks to the nullity plus rank theorem, F is neither 1 to 1 nor on 2. I reported here the matrix so we can analyze it more easily. One thing that you can do is to develop the determinant along the second row using a Laplace formula, and what you find is this computation here, which gives rise to 0. Hence, the linear map F associated to A is neither 1 to 1 nor on 2. However, there is a simpler way to see that the determinant of A is 0. In fact, in this theorem here, there is the list of the most important properties satisfied by the determinant. Property 9 says that if a matrix has 2 rows or 2 columns which are linearly dependent, then the determinant of the matrix is 0. In our case, it is very easy to see that the first row and the third row are linearly independent. In fact, you can check that the third row is just -2 times the first row. So, by taking into account this property here, we can avoid all the computations of the determinant through Laplace formula, and we can immediately say that the determinant of A is 0, thus guaranteeing that F is neither 1 to 1 nor on 2. Finally, let's consider the third exercise. Given these endomorphisms, establish if they are 1 to 1, on 2, or automorphism of R3 using their associated matrices. Recall that an automorphism is an isomorphism of a vector space with itself. The exercise ends with this question. Are the endomorphism G composed with F and F composed with G automorphisms of R3? My only hint for the solution of this exercise is to study the properties of f and g using matrices. Let's discuss the solution to exercise 3. Following the hint, we associate to the linear map F a matrix with respect to the canonical basis of R3. If we apply F to the three vectors of the canonical basis of R3, then we find these vectors here, which are the columns of the associated matrix. Since the second row of this matrix has two zero entries, we can easily compute the determinant of A by using the Laplace development along this row, and we find that the determinant of A is 2, which is of course different than 0, and so F is an automorphism of R3. We repeat the same reasoning on the linear map G. We apply G to the three vectors of the canonical basis of R3. We obtain these three vectors here, which are the columns of the matrix B associated to G, and we compute its determinant. We see that the second row of B has two zero entries, and so it is convenient to use the Laplace development along the second row of B in order to compute its determinant. This is exactly what I've done here, and we find again that the determinant is 2, different than 0, and so also G is an automorphism of R3. To establish if the compositions G with F and F with G are automorphisms of R3 or not, we have two strategies. The first is immediate and consists in the consideration that the composition of automorphisms is again an automorphism. The second strategy is longer, but it can be a very useful exercise for you. It consists in the observation that the matrix associated to this endomorphism with respect to the canonical basis of R3 is the product of B and A. Similarly, the matrix associated to this endomorphism with respect to the canonical basis of R3 is the product A times B. I strongly invite you to compute this matrix product and this matrix product. Verify that the determinant of this matrix and this matrix is different than 0, and so this endomorphism and this endomorphism are automorphisms of R3. So here we are, we have finally arrived to the last chapter of this course, dedicated to the solution of systems of linear equations. As you know, for me, it's always important to motivate why it's interesting to study a certain mathematical topic. In the case of systems of linear equations, that we will call for short linear systems, providing both practical and theoretical motivations is very easy. Let's start with two practical motivations. The first one comes from the theory of electronic networks. The question regarding this network is the following. Knowing that all the resistors, meaning R1, R2, R3, and R4, have an electric resistance of 10 ohms, and knowing that the two generators of electromotive force produce a difference of electric potential of 5 volts, what is the current flowing through the resistor R2, that is the current I3? Don't be scared, it really doesn't matter if you know how to deal with electronic networks or not. In order to solve the exercise, you just have to believe in the validity of the laws that I'm going to discuss, and you'll see that we'll arrive naturally to a linear system that will provide the answer to the question. First of all, you have to know that this point here and this point here are called nodes of the network. And there is the law of conservation of currents at a node, which says that the algebraic sum of the currents at a node is 0, which means that the incoming currents into a node must be equal to the outgoing currents. If we consider this node here, the law of conservation of currents says that I1 plus I2 must be equal to I3. That is, I1 plus I2 minus I3 is 0. I reported this equation in the next page. Now we have to consider Kirchhoff voltage law, which says that in a closed path of the network, the difference of electric potential due to the generators must be equal to the voltages through the resistors. The voltage through a resistor can be expressed by Ohm's law, which says that this quantity is the product of the resistance R times the intensity I of the current that flows through the resistor. In our network, we have two closed paths, also called loops. The first loop indicated in blue is this one here, and the second loop indicated in red is this one here. If we apply Kirchhoff's law on the blue loop, we have V1 equals R1 times E1 plus R2 times I3 plus R3 times I1. Now Kirchhoff law applied on the red loop gives V2 equals R2 times I3 plus R4 times I2. So notice that we have determined three equations for three unknowns, the currents. If we now introduce in these equations the data given by the exercise statement related to the resistors and the generator's voltage, we find this linear system here. If you follow what I wrote, you arrive to the solution of this system in terms of the three currents. And the answer to the question, what is the intensity of the current that flows through the resistor R2, is 0.3 ampere. Let me stress again that it's absolutely not important if you don't master the theory of electronic networks. With this example, I just wanted to show how linear systems appear naturally in the field of electronics. Now with this example, I'm going to show that linear systems may also appear in biology. In particular, in the example, we discuss the process of photosynthesis. During this process, plants use energy from sunlight to convert carbon dioxide and water into glucose and oxygen. So the chemical reaction of photosynthesis is the following. X1 molecules of carbon dioxide plus X2 molecules of water go into X3 molecules of oxygen plus X4 molecules of glucose. Now the question is, taking into account the conservation of mass, what kind of weights X1, X2, X3, and 4 make sense in this chemical reaction? Of course, what we have to do is to impose that the number of atoms of hydrogen, carbon, and oxygen on the left-hand side of the chemical reaction of photosynthesis is equal to that on the right-hand side. Let's deal with each element separately. We start with hydrogen. Notice that here we have 2 atoms of hydrogen multiplied by X2. So we write 2X2, and on the right-hand side we have 12 atoms of hydrogen multiplied by X4. So we have to write 12X4. In the case of carbon, we must write X1 alone equals X4 times 6. Finally, for the oxygen, we have 2 times X1 plus X2 equals 2 times X3 plus 6 times x4. As you can see, the linear system that we obtain is very easy to solve, and the solution is that x1 is equal to x2 and x3, and they are all equal to 6x4. Of course, x4 must be a natural number, so we impose that x4 is n. By using these values, we obtain this chemical reaction for photosynthesis, where n is a natural number. We immediately see that n equals 0 doesn't make sense because it corresponds to the absence of molecules. However, for each natural number strictly greater than 0, the chemical reaction for photosynthesis that we have written here makes sense. In particular, for n equal to 1, we obtain the canonical chemical reaction for photosynthesis, this one here. So this analysis shows that plants need at least 6 molecules of carbon dioxide and 6 molecules of water in order to perform photosynthesis. And when they do that, they release 6 molecules of oxygen and 1 molecule of glucose. Since a lot of the oxygen that we all breathe is produced by plants through photosynthesis, I can think of a better practical example to motivate the interest about linear systems. Besides the two practical examples that we have discussed, I also want to give you a theoretical motivation of why it's important to study linear systems. Consider two vector spaces V and W over the same field and a linear map F between them. Then fix a basis BV with vectors V1, Vn of V and a basis BW with vectors W1, Wm of W. Then we know how to uniquely associate F with a matrix A. In chapter 2, we have seen that if we decompose any vector V on the basis BV like this, and the image by F of V on the basis BW like this, then the relation between these coefficients here and these coefficients here is given by this matrix equation. If you perform explicitly this matrix product, and I strongly invite you to do it, then you can rewrite this matrix equation as this system of linear equations. So you see that linear systems are naturally associated with matrix multiplication, which, as I have already told you, has a major importance in linear algebra. In chapter 1 and 2, we have already encountered systems of linear equations. However, they were of small size, typically 2 or 3. It is clear that if the number of equations or variables increase, then we need a more systematic method to solve a linear system. Moreover, it will be ideal to turn this method into an algorithm to be run by a computer. We are now going to see that this is possible thanks to what we have learned in chapter 1 and 2. The precise definition of linear system is the following. A system of linear equations, or linear system, with m equations and n unknowns is written in this form here. And it can be rearranged in the so-called matrix form, this one here, where A is the so-called coefficient matrix with all entries given by the coefficients in front of the unknowns. X is the so-called vector of unknowns, and B is the so-called vector of known data. As you can see here, A is a m times n matrix with entries in a field F. For us, F will always be the set of real numbers. X belongs to Fn, and B belongs to Fm. If B is the null vector of Fm, written as a column vector, then we obtain Ax equals 0 which is the so-called homogeneous linear system associated to the linear system AX equals B. As always, let's immediately give an example. This is a linear system with 5 equations and 4 unknowns, x, y, w, and z. To write the matrix form of this linear system, we first need the coefficient matrix, which is obtained by introducing in an ordered fashion the coefficients of the unknowns. Pay attention to the fact that when an unknown doesn't appear in an equation, for example, the second one, then the corresponding entry in the matrix is 0. For example, here we don't have x, and so the entry corresponding to the coefficient of x must be 0. Same for the coefficient of z. The vector of unknowns is this one, and the vector of known data is this one here, corresponding to the column vector obtained by taking all the coefficients that appear on the right-hand side of the equations. Let's now see what we mean with resolution of a linear system. To solve a linear system in the matrix form AX equals B means finding at least an explicit vector x bar which, inserted into the matrix equation AX equals B, transform it into an identity, which means that the vector A times x bar, which belongs to Fm, coincides with the vector B. If the linear system AX equals B has at least one solution, we say that it's solvable. As always, let's illustrate the definition with an explicit example. This is a linear system. The matrix form of this linear system is written here, with this matrix being the coefficient matrix A. This is the column vector which represents the unknown, and this is the column vector which represents the known data. A solution for this linear system is given by this column vector here. In fact, if we multiply A with this column vector here, we obtain 2, 1, which is exactly B. The practical implication of this with respect to the original linear system is the following. If you replace x with 1 and y with -1, then you obtain, instead of 2 equations, 2 identities. Let's check it. So we write instead of x 1, and so here we have 1 and here we have 2, instead of y -1, and so here we have +1, and here we have -1. And so the first equation is 1 plus 1 equals 2, which is an identity, and the second equation is 2 minus 1 equals 1, again an identity. So by construction, having this matrix identity is exactly the same as having a system of identities. Okay, after these definitions, we start using what we have learned in chapter 1 and 2 in order to solve systems of linear equations. We start with this theorem here. The linear system AX equals B has a solution if and only if B belongs to the image of A. That is, if and only if B is a linear combination of the columns of A. Why that? Well, if we apply the matrix A on the vector X through matrix multiplication, we obtain B. Hence, if you remember the definition of image of a matrix, we have that B must belong to the image of A in order to satisfy this equation. If B doesn't belong to the image of A, then it can never satisfy this equation here. Moreover, we have seen that the image of A is the span of its columns, column 1, column n. Hence, B can be a solution of AX equals B if and only if it is a suitable linear combination of the columns of A. The second statement of the theorem says that the solution of the associated homogeneous linear system, that is Ax equals 0, coincides with the kernel of A, and so it is a vector subspace of Fn. Again, this is simply the application of the definition of kernel of a matrix, plus the fact that the kernel, we know it is a vector subspace and not a simple subset. Then we have this very important theorem, which says that if x bar is a particular solution of the linear system Ax equals b, then the set of all solutions of this linear system is given by x bar plus the kernel of A. This is, of course, the set of vectors that can be written as x bar plus a vector k belonging to the kernel of A. So, in practical terms, we can say that in order to know all the solutions of Ax equals b, it is enough to know just one solution of this linear system and all the solution of the associated homogeneous linear system. Differently from the previous theorem, the statement of this last theorem is not trivial at all, and so it's better to show its proof. The statement of the theorem is about the equality between two sets. This is the first set, which is given by all the vectors that can be written as the vector x bar, which is a particular solution of Ax equals b, and any vector belonging to the kernel of A. Instead, this is the set of all the vectors that turn out to be solutions of Ax equals b. A canonical proof of the fact that two sets coincide is to show that one is contained in the other. This is exactly what we're going to do. To prove this inclusion, we have to show that any vector that can be written as x bar plus k with any k belonging to the kernel of A is a solution of Ax equals b. To do that, let's apply the matrix A to this vector here. We know that this is done by performing the matrix product. By the additivity of the matrix product, we obtain that this can be written as A times x bar plus A times k. But since x bar is a solution of Ax equals b, we have that Ax bar is b. Moreover, k belongs to the kernel of A, so Ak is 0. So we obtain b. Hence, look what we have. A applied to x bar plus k equals b for any k belonging to the kernel of A. So this is a solution of Ax equals b. Now, to prove this inclusion here, we have to suppose that x prime is any solution of Ax equals b, and we have to show that x prime can be written as x bar plus k. The key to prove this fact is to consider the difference between x prime and x bar and to apply A to it. A times x prime minus x bar, again by additivity, is Ax prime minus Ax bar, but x prime is a solution of Ax equals b, so Ax prime is b, and x bar is again a solution of Ax equals b, so Ax bar is b. B minus b is 0. This means that this vector is nullified by the action of A. So, x prime minus x bar belongs to the kernel of A. Hence, it exists k belonging to the kernel of A such that x prime minus x bar is equal to k. And this leads exactly to what we want, because we can say that x prime, any solution of Ax equals b, can be written as a particular solution of Ax equals b plus a vector that belongs to the kernel of A. In this course, we are not going to use explicitly this result. However, it was important to discuss it because it plays a major role in the solution of linear differential equations that you will surely encounter during your academic path. Now we pass to the characterization of solvability of a linear system and to the determination of the unicity or not of its solution. In order to do that, we need to introduce a novel matrix. Given the linear system Ax equals b, we call the augmented or complete matrix of the system the M times n plus 1 matrix written here. Notice that the augmented matrix is simply obtained by providing A with a novel column at the position m plus 1, which is given by the column vector B containing the known data of the original linear system. We can now introduce the most important theorem related to the solvability of a linear system, which is called Roché-Capelli theorem. Let Ax equals b be a linear system of m equations in n unknowns, then this linear system is solvable if and only if the rank of A is equal to the rank of the augmented matrix. Suppose now that the linear system is indeed solvable. This means that there exists a natural number R, which is the common rank of A and of the augmented matrix. The theorem says that if R is equal to the number of the unknowns, then Ax equals b has only one solution. Instead, if R is strictly inferior than n, then the linear system has an infinite amount of solutions which depend on n minus r parameters. The theorem of Roché-Capelli has three important consequences. The first is that a linear system may have no solution, which corresponds to the case in which the rank of A is different than the rank of the augmented matrix. The second is that a linear system may have a unique solution, which corresponds to the case in which the rank of A is equal to the rank of the augmented matrix, let's call it R, and it is equal to the number of the unknowns. The third is that a linear system may have an infinite number of solutions, which is the case corresponding to the situation in which R is strictly inferior than n. In this case, we say that the linear system has infinite to the power n minus r solutions because there are n minus r free parameters. So you see that in the two cases of solvability, a linear system either has a unique solution or it has an infinite amount of solutions. So pay attention, if you find more than one solution to a linear system, it means that you can find an infinite amount of them. As I told you before, we are not going to use explicitly the theorem which says that all the solutions of a linear system can be written as the sum of a particular solution plus a vector belonging to the kernel of the coefficient matrix. However, be aware of the fact that this theorem appears here in the proof of the theorem of Roché-Capelli. Unfortunately, we don't have the time to discuss the proof, but as always, I strongly invite you to read it. In order to illustrate the three cases put in light by Roché-Capelli's theorem, let's see these examples. This system provides an example of a non-solvable linear system. Instead, this system can be solved with a unique solution written here. Finally, this system has an infinite amount of solutions. In fact, as you can see, the solution is written in terms of a free parameter. If you fix the parameter z to be 0, then a solution is 1/2 minus 1 and 0. But if you fix the parameter z to be 1, then you have another solution, which is -2, -3, and 1. But you can also fix z to be -2, and then you get 11.5, 3, and -2 as a solution. If you keep choosing values for the parameter z, then you find an infinite amount of solutions. With these examples, I just wanted to illustrate the three different cases allowed by Roché-Capelli's theorem. In the next section, we're going to study a method due to the great Gauss that will allow us to efficiently solve linear systems, and then we will apply the technique to explicitly solve the three linear systems that we have just presented.
It's now time to recap the information that we gathered about systems of linear equations. First of all, we have seen that it's very convenient to transform a system of linear equations in its matrix form. In the matrix form, A is the coefficient matrix, X is the unknown vector, and B is the vector of known data. The most basic information supplied by the matrix form is that the linear system has a solution if and only if vector B belongs to the image of the matrix A. The reason is that when this equation is satisfied, then B is secretly a linear combination of the columns of A, which we know from chapter 2 span its image. We have also seen that when we write the system in matrix form, we can also consider the so-called associated homogeneous system, which is written as AX equals the null vector. In this case, of course, X is a solution if and only if it belongs to the kernel of A. The importance of considering the associated homogeneous system is put in light by this result, which says that if we have a particular solution of the original system AX equals B, then in order to construct all the other solutions, we just have to sum this particular solution to the kernel of A. Another core result of the theory of linear systems that you must remember is the Roché-Capelli theorem, which says that the system AX equals B admits a solution if and only if the rank of the matrix A is equal to the rank of the augmented matrix. So, if the two ranks disagree, then the system doesn't admit any solution. Instead, if the ranks agree and they coincide with the number of the unknowns, then the system has just one solution. However, if the ranks agree but they are strictly inferior than the number of the unknowns, then the system has infinite solutions.
When in chapter 2 I introduced the concept of rank of a matrix, I told you that it was going to be very important in the sequel. The theorem of Roché-Capelli confirms that. In this section, we are going to discuss a technique due to Gauss that will allow us not only to solve efficiently linear systems, but also to compute very easily the rank of a matrix. Finally, and very importantly, this technique can be automatized by creating an algorithm that can be run on a computer. The method is based on the concept of matrix reduced by rows. A matrix A is said to be reduced by rows if, apart from the last row, in every other non-null row, there exists a non-null element below which there are only zeros in the same column. I'm perfectly aware of the fact that the definition of matrix reduced by rows is not the easiest one. So before going forward, let's immediately see an example. Let's consider this matrix here. The first row is non-null, and so for A to be reduced by rows, we have to find at least one element under which there are only zeros in the same column. We have that 3 and 1 have this property, as you can see here and here. The second row of A is null, and so we can forget about it. The third row of A is non-null, and we have to search for non-null entries under which there are only zeros. As you can see here, such an entry is provided by 1 in this position. Finally, we have the last row, but in the definition of matrix reduced by rows, we don't ask absolutely anything on the last row. To conclude, the matrix A is reduced by rows. Let's now see an example of matrix which is not reduced by rows. Let's consider the first row. We have that under 1 in the same column, we have the presence of a non-null entry. The second entry in the first row is 0, so we don't consider it. Finally, we have that under the third entry of the first column, which is not 0, there is a non-null entry. Hence, B is not reduced by rows. Now that we have provided two examples, let's get back to the definition. Every non-null element of a row that makes a matrix reduced by rows is called special. Moreover, every non-zero entry of the last row is considered special. Following the previous analysis on the matrix A, we have that all the special elements of this matrix are those surrounded by a box. By far, the most important property of a matrix reduced by rows is the following. The non-null rows of a matrix A reduced by rows are linearly independent, and so the rank of a matrix reduced by rows is exactly the number of its non-null rows. An immediate application of this theorem is the fact that the matrix that we have analyzed before, this one here, has rank 3 because it is reduced by rows and there are exactly 3 non-null rows. You can find the proof of the previous theorem written here, but unfortunately we don't have the time to discuss it. Let's continue with this definition. Consider a matrix A with m rows, n columns, and entries in the field F. Suppose that A is not reduced by rows, then reducing A by rows means to find a matrix A prime with the same dimension as A and with coefficients in the same field, which is reduced by rows and that has the same rank of A. We are going to achieve the reduction of a matrix by rows using the following three kinds of operations, which are called elementary transformations. The first kind of these transformations is by far the most important, and the other two kinds help simplifying the computations. Let's define the elementary transformations on the row of a matrix A of dimension m times n, and let's indicate the rows of A like this. The elementary transformations of the first kind on the rows of A, indicated with E1, consist in adding to a row a different one multiplied by a non-null coefficient. The notation is the following. The row Ri is mapped into the row Ri plus alpha times the row Rk, where I and j are two indices between 1 and m, I and k are different, and alpha is a non-null coefficient. The elementary transformations of the second kind on the rows of A are indicated with E2 and consist simply in the exchange of one row with another. The notation is the following. Finally, the elementary transformations of the third kind on the rows of A, indicated with the symbol E3, consist in multiplying one row by a non-null scalar alpha. and in this case the notation is this one. Now recall that the rank of a matrix is exactly the number of linearly independent rows which agrees with the number of linearly independent columns. So exchanging two rows or multiplying one row by a non-null coefficient doesn't change the relation of linear independence. So the rank of a matrix is totally unaffected by the transformations E2 and E3. We can ask ourselves if also the transformations E1 don't modify the rank of a matrix. This is not trivial, but it's guaranteed by the following theorem. As you can see, the proof of this theorem is quite long and we don't have the time to discuss it. In the next lesson, we will show how to use elementary transformations on the rows to reduce a matrix, and then we will deduce a powerful technique to solve linear systems.